Hello everyone, how are you doing today? Okay, so today we will start talking about electromagnetic waves. Right now you need to have your worksheet with you and start answering while you're watching this video. Okay, so let's start talking. This is a short introduction. And electromagnetic waves, we can't hear them or see them. Okay, there are different types of waves. Here are some of them. We have infrared, ultraviolet rays, microwaves, visible light, radio waves, and tiny waves that would be X-rays and gamma rays. Okay, we will see them one by one in the next slides. Okay, have you heard about them? Let's start. An electromagnetic wave is a wave that consists of vibrating electrical magnetic fields. A familiar example that will help you understand a little bit more are in the fields that make up an electromagnetic waves. Imagine, for example, a magnetic field. Okay, here we have a magnetic field. Because the electromagnetic wave would be the combination of these two. Okay, so this magnetic field, you can see, imagine a bar magnet, and you can see all of this is a magnetic field. Okay, because of its force field, a magnet can exert force on objects without touching them. They just have to be in the same space or magnetic field in order to feel that force or energy. And then we have an electric field, which is similar to a magnetic field. Here you can see one of the examples. And it's an area of electrical force surrounding a charged particle. Like a magnetic field, an electric field can exert force on objects over a distance without actually touching them. Okay, so as I said, an electromagnetic wave would be a combination on both of them. So when these two fields come together, they move through space or through any medium at the speed of light. Now, when particles change direction, a vibrating electric field is created and produces a vibrating magnetic field. Let's talk about vibration, okay? This is how the electromagnetic waves work. They vibrate a lot and they can pass through one space or another space, okay? Or as I said, through a medium. An electromagnetic waves begin when an electrically charged particle vibrates. When a charged particle vibrates, it causes the electric field surrounding to vibrate as well. A vibrating electric field, in turn, creates a vibrating magnetic field. And the two types would combine to create the electromagnetic wave, just as I said before, okay? A vibrating charged particle, which is just here at the left, generates vibrating electric and magnetic fields that we'll just see right now. These vibrating fields make up an electromagnetic wave. Now, before we continue, you need to make sure you understand that an electromagnetic wave is made of transverse waves. Okay? And as you can see, the electric and magnetic fields that make up an electromagnetic wave occur at the right angles of each other. Both fields are also at right angles to the direction that the wave travels. That is why the electromagnetic wave would be a transverse wave, as I just said, right? So here you have a magnetic field, the electric field with right angles, and the direction of the wave in one side, okay? And different than the mechanical transverse waves that we saw last week that require mediums, these ones do not require a medium. An electromagnetic wave can travel through space without a medium. Waves traveling through a medium lose some energy to the medium. However, when an electromagnetic wave travels through space, no energy is lost, so the wave doesn't get weaker as it travels. And you'll see right now some examples. However, this energy will be spreading out over larger areas and they will come like from far away, okay guys? This is similar to the way a sound wave spreads out, but it's just faster because it will be traveling at the speed of light. So there's two ways to explain the electromagnetic waves behavior, through the wave model or to the particle model. Now, scientists had like a little bit of discussions on how to explain it, because you would say, well, teacher, we're talking about waves, so it would be wave model, but the particle, and remember that light is also part of electromagnetic waves, so that was kind of tricky for scientists, especially for Albert Einstein. So the way they explained it was that when light passes through a polarized filter, waves vibrate in all directions. Polarizing filter has tiny slits in one direction, and light enters. That's what a polarized light would be. Now let me show you this example. And for example, here, you know what a polarized object is, right? Like the windows in a car or the sunglasses, they have really, really, really tiny spaces where the wave can pass through. Okay, this would be the wave model. Now, for example, in this one, the fence with vertical slits allows only waves that vibrate up and down to pass through. Okay, imagine this one is light, it would pass this way, okay? But vertical waves cannot pass through a fence or filter with horizontal slits, because this one is traveling through, and here it just can't continue its path, okay? Electromagnetic radiation behaves like waves of energy most of the time, but sometimes it behaves like particles, and there's where the doubt came. As evidence accumulated for this nature of electromagnetic radiation, Albert Einstein developed a new theory about electromagnetic radiation called the wave-particle theory, as I just said. This theory explains how electromagnetic radiation can behave as both wave and particle. And it says that when an electron returns to a lower energy level, it is thought to give off a tiny packet of energy called photon. Okay? The electron returns to a lower energy level and releases a packet of energy. And now, in the particle model of light, light behaves as a stream of particles. You've seen light, right? Like enter through a window and you see like small white beads. Okay, when high frequency light shines on metals, tiny particles move. Okay, when this light enters, for example, a metal, it will bounce back. We'll see an example right now. And light can cause electrons to move so much that it is knocked out of the metal. Okay, and this is what we call the photoelectric effect. Now, to explain it better, I want you to understand that if the waves look like this, depending on the type of wave, imagine a color wave to invisible light, they would absorb the energy differently. Let's watch this short explanation.
We're in the demo lab with Lonnie, where he set up a photoelectric effect experiment. He has white light impingent on a metal, and the energy of the photoelectrons emitted are shown on the meter at right. If he puts a red filter in the path, now only red photons can strike the metal, and you can see they do not have sufficient energy to eject photoelectrons. If we go to higher energy photons, say go to yellow light, that's shorter wavelength and higher energy photons, they may be able to eject photoelectrons. And indeed, photoelectrons are emitted, but with a relatively small energy. If we go to higher still photon energy, green wavelengths, that's shorter wavelengths still, higher photon energies, we can see photoelectrons emitted at a higher energy. Now we can still go to higher energy photons. Blue photons, photons in the blue region, are the highest energy visible photons, and Lonnie has a blue filter that will pass only blue photons. Putting the blue filter in the path, shows photoelectrons emitted at the highest energy. So here's an example of the photoelectric effect.
Okay, so light is a stream of tiny packets or particles of energy. And each packet, as we said, it's a photon. Okay? So what happens is like that the light comes here, and here we have this piece of metal, and the electrons bounce back. Okay? And this would be the photoelectric effect, as we saw right now. So before we continue, it's important to know that the most important source of electromagnetic radiation on Earth is the sun. Electromagnetic waves travel from the sun to the Earth across space and gives us virtually all the energy that supports life on our planet. Many other sources of electromagnetic waves that people use depend on technology like radio waves, microwaves, and X-rays are some examples, and we use these electromagnetic waves for communication, cooking, medicine, and many other purposes. Now, from this, we start talking about electromagnetic spectrum.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats.
Have you heard about the electromagnetic spectrum? Well, the electromagnetic waves travel at the same speed in a vacuum, differently than the other types of waves that we saw before. For example, sound. They will refract and change their speed. This one in a vacuum will travel at the same speed. Let's just understand that vacuum is a space that contains no air or other gas, for example, at space. And to understand better the electromagnetic spectrum, you need to understand how the waves are managed there. And there are different wavelengths and different frequencies. Remember what a wavelength is? Remember what a frequency is? Some of them that are included in the electromagnetic spectrum would be visible light, radio waves, which have longer wavelengths, or those that have shorter wavelengths, like X-rays. This is exactly what an electromagnetic spectrum looks like. You can see how the waves that are right here are longer and these ones are shorter. Okay? It means that if in this side they're shorter, the frequency is higher. And in here, if you want a period of time from here, for example, to here, and compare that same size from here to here, where would you have more frequency, more hertz? In this part right here. Yes? Okay, another important thing is that from here to here, there are more dangerous electromagnetic waves, okay, like cancerous. So we need to be very careful when we're near them. And from here to here, there's not a scientific law or comproval that will do us any harm. Okay, so important, the lowest frequency will be right here and the highest frequency on this side. The longest wavelength in this side and the shortest wavelength in this side. Let's remember what a wavelength is, from crest to crest or trough to trough. Okay? Let's start with radio waves. Radio waves are those with longest wavelengths and lowest frequencies, or short or smallest frequencies. We use them in broadcasting to carry signals for radio. Radio stations, what they do is they send a signal from here, and then through these radio waves, they convert to electrical signal into the radio, and the radio converts it into sound waves. Okay, and that's how you can listen to the radio station. Okay, and these radio waves manage different types of waves.
How does a radio work? The longest waves on the electromagnetic spectrum, radio waves, carry information from a station to a receiver. But radio waves don't carry information all by themselves. They need to be altered or modulated. A signal, a transverse sound wave, overlays the carrier wave, forcing it to change. There are two ways radio stations modulate their carrier waves: amplitude modulation, or AM, and frequency modulation, FM. AM radio broadcasts a carrier wave that maintains a constant frequency, while the overlaying sound wave modulates its amplitude. And FM radio maintains a constant amplitude, while the frequency varies based on the overlaid signal. AM and FM radio carry sound waves, a type of analog signal, to your receiver. Modern digital radio carries information as a digital signal, coded in the form of numbers. Millions of radio waves, carrying sound wave signals and digital signals, reach your receiver every second. The receiver's tuner picks out a specific signal. Its amplifier strengthens that signal. A demodulator separates the signal from the carrier wave. And then, a speaker converts the signal to the sound waves that you hear.
And this is how AM and FM radio waves work. Now let's talk about microwaves. Microwaves have shorter wavelengths and higher frequencies. They're used commonly in microwaves. Okay, what these microwaves do is that with their motion, they start moving the particles of the food. And remember, when there's more kinetic energy in particles, the temperature will rise, and that's how microwaves work. And in cell phones, also microwaves are used. They are converted from electrical to microwaves to go around the space, okay, and until it gets to another cell phone. Also, radars use microwaves. A radar will be a radio detection and ranging, okay? And these radars they are used to detect objects. Have you seen them in, for example, police officers seeing how faster is a car moving and then give you a ticket? They measure the distance and the speed of an object, okay, in this case cars, and they send microwaves that reflect off an object, and so the time it takes for the reflected waves to return are used to calculate the distance. And they use the Doppler effect. Do you remember we saw the Doppler effect last week? Okay, so this is what happens. The person is right here, the police officer. They send the waves, and the time that they come back, they would have your speed. So the difference in the frequency is just to calculate the speed. Now we have infrared waves. The infrared waves are those that you can feel the energy of the infrared rays as heat. For example, if you go to the beach, you can feel some warmth from the sun, and that's called the infrared waves. Commonly in the industry, they use it to keep food hot or warm. So warmer objects give off infrared waves with more energy and higher frequencies than cooler objects. Here is the example I was talking you about. And to see how infrared waves are on a certain object, you use an infrared camera. Do you have cameras at home? And you can see that you can watch them through the night, a person walking through the night in the room. Okay, and the image that you can see are also called, it's called the thermogram, okay? And the higher temperatures, they're brighter colors, okay? For example, the hands here have a higher temperature than the spider, okay? Here, the nails have a higher temperature than the rest of the hand. Now we have visible light. In the electromagnetic spectrum, the visible light is really a short, super short space, okay? And well, as I said, it's a small part of the electromagnetic spectrum, and white visible light would be a mixture of many colors. Light waves bend or refract when they enter a new medium, okay? And white light passes through raindrops. For example, that would be another example of visible light, and that would form a rainbow. Have you seen them? That's how they work with electromagnetic waves at the electromagnetic spectrum, the part of visible light. Can you describe other times when you have seen the visible spectrum? I'll give you one. For example, a CD on the wall. Due to the light passing through a glass, you can see the visible light of an electromagnetic spectrum. Now we have ultraviolet rays, and here is where we start going to dangerous paths, okay? It has higher frequencies and carries more energy. This energy can damage or kill living things. Too much exposure to these ultraviolet rays that come from the sun can cause you skin cancer. Now, it's also good to your skin, but do not exaggerate, okay? It's just what I just said here. Small amounts are useful. Skin cells produce vitamin D and healthy bones and teeth. And then we have X-rays. Have you had an X-ray before? They carry more energy than ultraviolet rays. And they can penetrate most matter, even bones or lead. Okay? That's why when you break your bone and you go to the doctor, they put you like a vest on your chest to don't let the X-rays pass through. Engineers use it to find a crack on a building. Too much exposure to it can also cause cancer. Now let's talk about wireless communication. Radio waves carry information from antenna to antenna. Pay attention to this because it comes on your worksheet. And this is what we were talking about earlier. Broadcasting signals, amplitude modulation and frequency modulation. Changing the amplitude of the wave would be for the amplitude modulation, and changing the frequency of the wave would be the FM, okay? You can see it in your radios, for example, the football of Tigres and Rayados, you always hear them in AM, right? So amplitude modulation can be broadcasted over longer distances, and frequency modulation not that far but has a better quality. And have you seen that? I don't know if you, because you're always listening to Spotify and so on, but like to understand more or less, ask your parents what's the difference between these two of them. And then talking about satellite communication satellites work like receivers and transmitters of a cellular phone system. Okay, outside of the Earth, there are satellites, and the waves bounce back and forth to all parts of the world that you can communicate. Communication satellites receive radio, television, and telephone signals to receivers on Earth. With a satellite phone system, you can call anywhere in the world, but it costs more than using a cell phone. Okay? Have you seen, like in movies, that they have a special satellite cell phone, a really, really big one, like the CSI police officers and all of that they can even communicate on top of an airplane? Okay, those are specialized phone systems. Radio waves are sent up, the satellite transmits the waves back. That's how it works. In the television system, customers need a satellite dish or antenna to pick up the signals and a decoding box to unscramble the signals, okay? That's, for example, what Dish uses, or Easy, those boxes that were the wireless also is distributed there at home. Well, that is just what I'm talking about. TV signals are sent up, and the satellite transmits the waves back with radio waves again. Then we have something called the Global Positioning System. Have you heard about it? I believe that yes. Global Positioning System, as the initials say here, is a GPS. It was originally designed for the military, and it's a network of 24 satellites that broadcast radio signals to the Earth, okay? And gives you an exact location of anything. Right now, all of your cell phones, your iPads, the cars have a GPS system. Okay, it's just what I said right now. Cars, airplanes, boats, cell phones. There's also some dogs that they insert a chip into them, and they have a global positioning system so they won't get lost. And 3 satellites can tell you where you are on Earth's surface, okay? The 4th one tells you how far above the Earth's surface you are. So For example, here you have one tower, one satellite, here you have another satellite, and here you have another satellite. And the combination of these three will tell your exact position, and the fourth satellite will tell like in the height you are. Okay? And for now that's it. I hope you can answer all of your worksheets, and if you have any doubts, please let me know and I'll help you answer it. Thank you guys. Have a great day.